Davide Crepaldi from SISSA. It's special because it's kind of different from the other talks that we have heard so far, which were more on computational linguistics kind of field. And so whereas Davide will, I think he's the right person for a seminar here, because he really kind of puts together all different kind of research that are going on at CIMeC. So the things they work on mind, brain, and language. And how we got to know each other? Well, it happened at Marco Marelli's wedding. So it was during a nice dinner. And I thought, isn't this guy's interesting? And then I met him again in a coffee break during the conference. And I thought that there was something nice in the chat, so then I went to look on his website and I discovered that indeed he's doing extremely interesting research, and that's how the idea of inviting him came. And so I discovered that he also got his his rich man, so he's perfect, working on ESC that is just starting, more or less. And I guess he's going to speak about this. So let's thank him for being here.
Thanks a lot, Raffaella. Thanks a lot. And thanks everyone for coming and for inviting me. I'm very happy to be here talking about what I'm doing right now. Yeah, as Raffaella was anticipating a little bit, today it's going to be a little bit of a talk, a mix of things. So it's going to be partly what I've already done, so some data to show you and to talk about, but also substantially about some ideas that I get out of this data and that still need to be tested. So it's supposed to be very interactive, and if you have any feedback at any point of the talk, I'm very happy if we interact while on the go. Okay, so as you see, the title is The Reading Brain of Statistical Learning Machine. It's a very provocative title. As you will see in the end, I will not conclude that that's really the whole story, as you may imagine. But I think that it's provocative point of view. Provocative in the sense that can provoke new research and probably can allow us to see things from a slightly different perspective as compared to what has been done in the past, which may, or may not, we will see, reveal interesting parts of the visual identification system. Word visual identification system, obviously. Okay, so as many travels and many trips and adventures in research, things start from a puzzle. Okay, so I have a little bit of a linguistic background. I'm not, properly speaking, a theoretical linguist and even less a computational linguist. But the few things that I've learned about linguistics when I studied it was that you cannot have morphology if there is no meaning involved, right? So morphology is about meaning. I will get into that a little more into the detail in a second. I just want to highlight the problem right now, that at some point in psycholinguistic literature there were a bunch of data, and very consistent data, so replicated many times in different labs in different languages. They were actually showing morphological effect apparently without any contribution from meaning. And this seems like a difficult thing to basically get your head around, right? So let's start the story from the beginning. What is morphology? I'm not going to spend too much into this for two reasons. Why? Because I'm definitely not the most entitled person to talk about this from a theoretical point of view in this room. So I would quite surely embarrass myself at some point. Second, because today I'm not going to go too much into the details of the theory behind. So pretty much the whole story about the morphology that I'm going to use today is this: that morphology is the thing that distinguishes between words like people and words like deer. This is how much linguistic theory I'm going to put today into my talk. Forgive me about that. You will see we'll get back at the end, which I think is also quite interesting. So basically the story is that in the case of words like people, you have it's basically very difficult, or probably even impossible, someone would argue, to decompose the meaning of the word into sort of well-identifiable part that can then be traced back into part of the form of the word, which is instead the case for dealer, right? Dealer is someone who deals, and the fact that the meaning of dealer is from one who deals, you can get it from two well-identified parts of the word, right? There is a deal, and there is ER, which kind of consistently indicates someone who does something in English, okay? So in a way, you can reconstruct the meaning of the word based on the form, to some extent, which is clearly not the case with people, okay? There are obviously many reasons why I think this is very interesting, but what I'm going to focus today is only one of these reasons, and it's the following. The morphology can be thought as of constituting a break into the classic arbitrariness that everyone assumes about language, right? So one of the other very few things that I was, very few clear things that no one would have any doubt about it when I was studying linguistics, is that the language is, to a great extent, is not iconic. So there is nothing that is intrinsically related to the form that you use in language that can give you a cue about the meaning of that word, right? So if you take elephant, table, hit, drum, you cannot see any connection with the meaning, right? So the fact that the elephant is called elephant, it could have as well be called peep, or whatever you like, and it would have worked fine, okay? As soon as we agree on how we use the labels, there is nothing into the labels that directly cue you towards the meaning. Of course, there are exceptions to this, but people tend to agree that to a large extent, language is like that. Now, if I ask you, though, what is the meaning of these two words, right? Of course, you may know it, of course, but imagine you're at the stage where you're learning English and you don't really know, and you go to a supermarket and buy a thing that you want to buy and then you want to eat for dinner, and you see that on the top of that there is it that you're supposed to preheat this thing, right? Even if you've never heard the word preheat, you won't pretty well understand what that means, right? You know that there is something that happens before something else, and that this something is the act of heating, okay? And the same for juicer, right? This is actually one actual example from my life when I saw this example in a paper, and of course I didn't know what a juicer was, but I didn't even stop at that word because my brain was sort of implicitly computing the meaning for that. Not very precisely, because for example this is not a person as opposed to dealer, but you can understand that there is an object that does something that is indicated in this case by the stem of the word, okay? Someone who produced juice. In this case, something that produced juice, okay? So there are connections. And there again, you can see that in this case, the form and the meaning are not really completely arbitrarily associated, okay? There are indeed cues in the word that can tell you something about the meaning. It will never tell you the whole story, or very rarely so, but there are connections. So this is clearly very different from elephant, table, heat, and whatever you want. An element that I think confirms very well this idea is that if you take the lexicon development historically, it has been computed recently, this figure, at least for English, I think. I don't know how much this is generalizable, but intuition is very, it sort of matches the intuition of the native speakers of any language, is that morphology is a prominent way in which language is developed. Okay, so like 70% of the new words entering English in the last 50 years were morphologically complex, and were coming from some sort of transparent combination of existing morpheme. Okay, think about bioweapon or guesstimate. Again, you may have never heard about the word guesstimate, but everyone has a clear idea in their mind what that could mean. Or even better, things like untweet, which I think, by the way, doesn't really exist. But anyway, again, you can have an idea of the meaning about that word. So if you want, there is a connection between the two words, form and meaning. They are typically arbitrarily associated, sometimes not so arbitrarily. And of course, the brain jumps into it, right? So the brain is a fantastic statistical learning machine, and there are many different examples of how the brain is able to build basically the knowledge that it uses to process language on the structure of the word. So for example, I'm going to be very quick here, there are word learning experiments that prove basically that you can generalize the information that you can acquire morphologically, okay? Here I'm putting, for example, the paper by Marcus in '92 where they were showing that kids that, well, actually children, tend to over-regularize what they learn during the language, or the quite famous morpheme frequency effect. So the time that it takes to you to identify a word is proportional to the frequency of their morphological components. Again, this is another sign that our brain actually sees the structure behind the word. You get interference effect with non-words. We will get to that later on. So if I give you an lexical decision experiment, something like shootment, it's going to be quite difficult for native English speakers to reject that stimulus as a non-word. because it could, it could bind together quite well, and you could even attribute a meaning to that in a relatively easy way, right? Although that's clearly not an existing word. And then you have the phenomenon of priming. I don't know how much you're familiar with that, so I'll go quite quickly over it, which basically essentially shows that if you have to do something on a word at a given time, and I show you just before that event a word that is related to it, you're going to be typically quicker or slower in some conditions, but you're going to be sensitive about the relationship between these two words. And when this relationship is morphological, you get a clear advantage. So if I give you dealer and then right after that the word deal, you're going to be quicker in processing deal as an effect of the fact that you've been exposed to dealer right before that. Okay? But of course, this fact per se doesn't prove much about the existence of morphology, right? Because if you think about it, dealer and deal not only share their morphology, they share lots of other linguistic level of description, right? So they are formally similar, similarly to will and deal, where the similarity in form doesn't come with any similarity in meaning. And they are also similar in meaning. So you could think that they are comparable to things like by and deal. So what psycholinguists typically do, they run experiments where they have all these conditions together, and they typically tend to show, that's quite reliable results, that the priming effect that you get for deal or deal is larger than the effect that you get from will and deal and by deal. So the fact that you cannot basically decompose the overall morphological effect into a component for the meaning and a component for the form, it's sort of a sign, it's typically being considered as a sign of the fact that you have some morphological representation in your brain, and that you use those morphological representations when you see these complex words going on. Interestingly though, language is so nice for this kind of accident that you can get. You also get something like corner and corn, right? Would you say that this is a morphologically complex word, that corner is morphologically complex? Even if you know nothing about morphology, just guess. No. Okay, we all agree. I would also say so. And in fact, the first experiments on morphology that I ran, this condition was actually the control conditions for deal or deal. So we consider, for example, in my case, I come from a mainly neuropsychological background, we consider aphasic patients to be sensitive to morphology only if they were bad here, but not here. Okay? So that it's the perfect condition. You have exactly the same sort of structural relationship between corner and core and deal and deal, but you're missing the semantics. And then guess what? After you're a PhD student, you run 4 years of experiments based on this opposition, and then you find out that somebody else has done exactly your experiment showing exactly the opposite results. And you start crying. You will get over it, don't worry. In this particular case, what happened? That at some point, people was using a particular form of priming, which is the masked priming paradigm, where you have exactly the same structure that I was telling you about. So you show a word that is related to the word that is coming just next. Okay? The only difference here is that this series of visual events happens so quickly that you become completely unaware of the presence of the prime. So you've been shown this sort of visual mask for half a second, and then you get the prime word for very short time, between 30 and 50 milliseconds, and then you get the target. And then you have to do something like, I don't know, lexical decision typically. You do not even notice that there's a word before deal, right? And still you get very, very solid morphological effect. At some point someone was using exactly my same logic, okay? So I want to show that there is masked morphological priming, so I need to have this condition. But I also need to have the corner-corn condition, right? And I'm claiming that I get genuine morphological effect only if I see a facilitation here that is different from the facilitation that I see here. Okay? Otherwise I could just say just form. And then, quite relevantly in this condition, people also have this third condition in which you have dialogue, right? So you see that here the form overlap is identical. So you have the entire target included into the prime. The only difference between dialogue and corner is that if you take out the stem, what you're left with is an existing morpheme somewhere in the language here. ER means something. And in this case, you're left with OG, which is never a morpheme in English. So OG is not ever associated to any systematic meaning in the language, right? So at some point, people started running these kind of experiments. Someone guess what happens? Do we get a difference between dealer, deal, and corner, corn? Yes, no? Yes. Somebody for no? You know what it is. You don't count. Exactly. This is exactly what happens. The opposite that people was thinking. So you get a substantial effect in dealer, deal. And notice that this is very different from here, from the real form condition, where you have no sort of morphology to speak of, but corner goes together with dealer deal. And that's very strange, right? So linguistically, these results do not make any sense. And so people struggled for years. What the hell does this mean, right? So why should be the case? Notice that this doesn't even make much sense in terms of behavioral linguistics, so more from the psycholinguistic point of view. What kind of advantage would you get into thinking that corner may be someone corner? So that's not the meaning that we're aiming at. So this is only slowing us down, right? So what could ever be the meaning of these results? Well, today we're going to explore one possibility, which is at the basis of the proposal that I'm telling you about. And this possibility is basically gets back to the former consideration, that the reason why you get this effect is exactly because morphology provides some shade of regularity into an otherwise mess. You have no idea how form correlates to meaning, but you notice that morphology brings some order there. And so your system may be able to capture these regularities and build on them. Particularly, think about pure visual word identification. So think about purely the form side of the story. Corn is a morpheme. What does this mean? That basically, the letters C, O, R, and N will occur together in the language quite frequently. More frequently than other sort of random organization of letters, like C, A, R, N. They are surely less frequent than C, O, R, N. So basically what the morphology is bringing is regularity, not only in the correspondence between form and meaning, but even at the pure form level, it allows you to make some prediction of what's coming next. Okay, so morphemes are also frequent chunks of letters. The brain notices that, develops some sort of representation, and takes advantage of this. Okay? That's pretty much the working hypothesis. Here I put just a very simple illustration of my case. What I've done here is to generate 16, well, 16 is just obviously an arbitrary number, 16 chunks of letters. Some of them are morphemes, and are the ones that you find indicated in red. They are put here on the x-axis. On the y-axis, you have the number of words in which these chunks appear. And as you can see, the morphemes are quite systematically towards the end of this distribution. So the morphemes tend to appear in more words than other random chunks of letters. This is of course a very simple illustration. I take these 16 things completely arbitrarily, but obviously then we run some sort of more in-depth analysis, and the results just hold. They follow the intuition that morphemes tend to be frequent chunks of letters. Okay? So from this, the main story for today. Maybe what's playing around here is basically some sort of statistical learning. Right? So the brain, again, is noticing these regularities in letter co-occurrence and is building on these regularities to provide prediction in a way that makes their perceptual identification of words a little bit quicker and a little bit less error-prone. Okay? This gets back to the 50s or 60s, right? The old idea of chunking, the magic number 7 of Miller, this kind of stuff. Right? If you can pack your information, if you can reduce the memory load that you can have, then you get some advantage. Of course, you cannot pack everything, because our experience is so diverse that we will never be able to make sense of everything that we need. But we can notice some statistical regularities in what happens to us, and when two things get together, they get associated. Maybe this is one of the prominent mechanisms that is behind visual word identification, and maybe that's the reason why you see this strange corner-corner effect. Okay? Taking things a little bit more general, this is gonna be the new approach to reading that I would like to explore. So the scripts, alphabets can be seen as fully fledged visual systems. In the end, that's what they are, right? Visual objects, things that hit your retina, just as much as chairs, tables, and anything else. If they are so, they can also be studied as such, without necessarily much contact with language real, right? With the semantics, with the syntax, with what makes language special. Okay? If that's the case, maybe the way we learn to deal with them can be captured by general perceptual mechanisms, for example, statistical learning in this case. And maybe, and this is going to be the most interesting part, also the way we learn to map the form onto the language realm, onto the meaning of things, can also be captured somehow by statistical regularities. By assuming that the brain is sensitive to this sort of co-occurrence structure that you get in the input, and then basically builds on that to help its own work. Okay? So this was the part of the talk that was sort of developing the idea. Now what I'm going to talk about are three, if I remember well and if I have time, three completely different bunches of data that to me really sort of support this idea. And at least I think they would suggest us that it make it worth to explore it. First thing, positional constraints in morpheme perception. Okay, this is going to be the most strictly speaking psycholinguistic part of the talk. What do I mean by that? Well, morpheme have positional constraints, right? So suffixes tend to happen at the end of word, or at least they follow the stem. They are never before the stem, right? So you see kindness, but you never see things like ness kind. Same for prefixes, just the other way around. Okay, you have pre-hit, and you never have hit pre. Interesting. Thanks God. We also have compounds, and compounds actually sort of break down these regularities, because if you consider three stems in this case, you can see that they can appear pretty much everywhere. So you have catwalk, but you also have wild cat. So cat can happen to be at different positions within other words. And this is by no means a trivial thing. I mean, it's obviously trivial because everyone can do it very easily. But if you don't code for position, then you're not going to be a very proficient language user. Because the language, maybe not Italian, but lots of other languages are full of these things. Morphological anagrams. So the two words hangover and overhang, identical morpheme, and of course it's quite critical that you remember what comes first, right? You don't want to go home to your mom and try to hidden an overhang from the previous time, right? So, what's the hypothesis? That maybe the system, the visual identification system, is building on these regularities. So it's capturing information in a way that makes us searching for the right thing in the right place. Which basically means that if suffixes happen to be at the beginning of words, we just ignore them. We do not think they could be suffixes. We do not identify them as units. This was the idea behind this experiment. I've mentioned a little bit quickly at the beginning of the talk this morpheme interference effect. Basically, the morpheme interference effect is what you get from these two conditions. This has been shown, tons of times right now, so it was nothing new on my side. If you see stimuli like gas pool, this is going to be difficult to reject. This is a non-word, so if I ask you to do a lexical decision, you should say no. But because the word is made up of existing morphemes, it is well formed, it can even be associated to a meaning, I would say, then it becomes quite difficult for you to say no. You've got to be slower, as compared to like an orthographic control such as gas fill. Then the prediction becomes quite obvious, right? So what happens if you flash around things, and now you compare full gas versus fill gas? If the morpheme identification is just the same, you should predict here exactly the same effect that you see here. So you should predict that full gas is lower than fill gas. If instead you're really blind to suffixes in the wrong position, then this full is never going to fool you. You're never going to misunderstand this as a suffix. And then this word is probably just going to be as difficult as this one. Okay?
Can I ask you a question?
Sure.
In this case, when you swap these parts, aren't you also killing the positional bigram frequency?
Yeah, you also are. We took that into consideration, and we had basically, we're quite lucky because, in principle that's what happens. But we were able to find a set of stimuli for which the transition was something like LG here. So, some sort of less frequent than this one, okay? Basically, we took it into account this effect and we sort of matched it. But yes, in principle, that's also what happens. There's another very obvious thing that happens here that I'll show you in a second that doesn't play much of a role, is that you're destroying the pure semantic interpretability, right? Independently of the morphology. If I ask you what kind of meaning you would associate to any form, in general there are things that would suggest you some meaning, right? And morphology is exactly, well, that's the essence of morphology, right? So here, I think you can quite easily build up a meaning. Here, of course, you can't. So we have measured that with some ratings with the participants, and I'll show you in a second that this doesn't correlate with the effect that you get. So it seems that semantics per se, like just how much you think something may mean something, is not playing a big role. And here are the data, okay? So you see that we replicated the classic interference effect, gasful slower than gasful, this is response time. And these are non-words, so this is what you expect, that you should be slower in rejecting gasful as a non-word as compared to gasful. But when you swap the morphemes, the effect just goes away. Okay? Then we need a second obvious thing to do. We also have the same thing for prefixes, because of course you cannot exclude just based on the previous experiment that it's something special about the beginning of a word, right? You don't want to see strange things at the beginning of stuff. Very basic alternative explanation. Not very plausible, not very interesting, and that was also what the reviewer thought, so we had to run another experiment. But we are lucky and we also have prefixes in the language, right? So we could do exactly the same effect, just all symmetrical. So now we have pre-hose versus pli-hose, and we just flip the two morphemes around. And you get exactly the same story. Okay, so pre-hose, the entirely morphologically built up word, non-word, is very slow as compared to pli-hose, but the difference goes away if you consider host pre versus host play. So it really seems that for prefixes and suffixes, that is, for those linguistic units that actually have positional constraints in the language, the brain is sensitive to that. And even build morphological representation that only works when they are in the right place. Okay? Then again, rather obvious follow-up for this. Let's go to stems. Sorry, this is a bit quick. Let's go to stems, right? I showed at the beginning that stems do not have the same constraints. So that stems can sort of happen pretty much everywhere. So if that's true, we should also be able to find evidence that basically show that when you swap around two morphemes in a rather unusual way, still these morphemes, if they do not suffer from positional constraints, they should elicit some activation at the lexical level for the corresponding word. I'm using this experiment to explain, which is a little bit more clear. So basically what we have done, this time was priming. We had real words as target, such as goldfish, and we were trying to, compounds obviously, and we were trying to prime these words by using the swap morpheme version. Okay? So fish gold, priming goldfish. Again, the prediction was, as I just said, because fish and gold are free stems, they do not suffer from positional constraints in the real language, so that the brain shouldn't have developed any positional constraints in this case. And so if you see the two morphemes swap, you should be able to identify them, and you should also be able to see some interference with the corresponding lexical entity. Okay? And then, of course, we had an unrelated condition just to measure the priming, basically. And we compare this with a condition in which you have a monomorphemic target, right? So if you forget about the morphology, fish gold and goldfish are also just similar at a purely formal level, right? So we need to make sure that this is really dependent on the morphological status of the two halves that were swapped. So we had a condition like tone bari, priming baritone. Exactly the same level of form overlap, but this time no morphemes involved. And this is the result that we get. Sorry that I changed the example here, I always forget to fix this slide. So basically what happens, here again you have response time. The dark gray is the related condition, the light gray is the unrelated condition. So the priming is tracked by the difference between these two bars. And in the morphological condition, you see that fire backfire determines a slower reaction, a quicker reaction time, so a large priming effect, as compared to its control condition. If you go to the orthographic condition, you see nothing, or if you see something, you even see the opposite effect. Now I'm not going to go into the details, but that's also quite in keeping with with the orthographic literature, which shows inhibitory effect for things that are similar to time. Okay? So if you want to wrap up the story, basically, yeah, this goes in the direction that we were sort of hypothesizing at the beginning, right? So there are positional constraints. When there are, your brain captures them. When there are not, your brain, of course, doesn't capture, which sort of, I think, resonate quite well with this idea that what you're doing is really sort of being sensitive to regularities in your language input and building representation, which of course then become fully fledged real linguistic representation, but at the purely perceptual level, they are just influenced by all these regularities that were captured by the brain. Of course, all these experiments, if you want, are quite shallow in a way, right? So, I mean, imagining that we don't see ness as a suffix at the beginning of a word is not particularly surprising, right? But of course, there are many, many interesting things that now we can do, now that we have established a baseline. First of all, is it about word boundaries? So is it about the suffix being at the end? Or is it about some sort of more local constraints? So how the morphemes really get together in which direction? We don't know. With these experiments, we can't really tell because we only use 2 morphemic words. So the stem that was, the suffix that was not identified, for example, was both at the beginning of a word and before a stem. Which one of these 2 is the one creating the effect? Is it this because at the beginning or because it precedes the stems? We don't know. Even more, and I think this is even more interesting, this kind of statistical constraints, exactly because they are statistical, are very frequently not all or none stuff, right? Even in free stems, if you think about it, there are many free stems that can be everywhere in principle. But that particular one happened to be very often at the beginning and very rarely at the end. So if the brain is really capturing all these regularities, it should be able to code for this. So for free stems, it shouldn't be all the same. We should be able to see that, as you say, the constraints are actually graded, because that's how our linguistic experience is. Our linguistic experience is graded. It's rarely black or white. There are instances, of course, of black or white suffixes and prefixes, but the free stems you should be able to see some modulation, right? So if I give you a pseudo compound in which the 2 morphemes are really in their typical position, that should be very difficult for us. Way more than the same exact pseudo compound, but where the morphemes happen to be in a very strange position for them. Very rare. Maybe attested in the language, but not frequent. Okay? And this is what we are testing now. Okay, end of the first part of the story. Let's move to my second strongest supporter, the baboons, which apparently were able to develop some orthographic representation. Okay? I'll show you why. I was hoping to show you the entire video. It is very funny. But I mean, it's not really critical. But it's curious to see what kind of experiment this guy were doing. So it's going to be a silent video, but at least you can see what the baboons were doing. So they was basically playing around in an enclosure, then from time to time they went into this booth, and this is what happened when they entered the booth. Something is going out of here, but you're never going to be able to listen.
And a quick dispenser to deliver a word after each correct response.
So they have a screen in front of them. Real English words and real English non-words happen, and they have to decide whether this is a word or not. And if they are good, they get some peanuts.
This unique facility allows us to collect data for several thousands of trials per baboon each day in optimal conditions with no stress to the animal.
They actually seem to have fun. Not even not the instance.
Certainly, reading is one of the most complex skills that humans have to learn.
Let me see if I can do something that you don't. Aha, here you see better. Okay, that's the screen that they were seeing.
If the letters formed a real English word, or cross-shape if the letters were not a real word.
Sorry, the contrast is not
The
very
key to
good.
success in training baboons to discriminate between real words and non-words is that each new word the baboon had to learn was repeatedly presented intermixed with different non-words.
Okay, I'll stop here. I mean, the point is not looking really at the whole story, but just to give you an idea of the experiments set up. So these baboons were just going there and just doing lexical decision just as much as our undergraduate student. Okay? They show stimuli, they have to press two things, one whether this is a word and one whether this is not a word. Of course, as you can imagine, this is a purely visual task for them, right? I hope everyone agrees they do not have any sort of very well-developed language. Okay? And this is their performance. So, words and non-words, each single line is a different baboons. On the x-axis, you have the training sessions. Of course, they stay there for for weeks, so they could collect many, many different sessions. Basically, when they were hungry, they just went into the boot to get some peanuts. And this is the performance. Okay? So as you can see, it doesn't take long before they start performing very well above chance. Okay? So at some point after, I don't know, probably 4 or 5 training sessions, all the baboons were consistently performing around 75% correct on the word trials, somewhat worse on the non-word trials, so sometimes they were thinking that non-words were words. But again, even here, you can see that they stay very much consistently above chance. Okay? Clearly not a human performance. Our undergraduates are way better than this. And yeah, we don't have to spend a fortune on peanuts. That's good. Good point. But yeah, they were actually learning something, okay? So they were not being completely a chance for the entire duration of the experiment. Maybe the first lines they were able to listen to the video notice that Jonathan Granger, the author of this work, was also mentioning that the little trick to have the baboons learning effectively was that the real words were repeated more than once during the course of the experiment, which was never the case for the non-words. Okay? This is the fix that it was necessary, and of course you can think, okay, so this is just memory, right? So they just when they see a word and they have seen that item already, they know that that's a word. So they're just disentangling things that happen to them more than once versus things that happen only once. Okay?
And the color was the words were colored, but the color were random.
The color were random, yeah. And I think it's actually the screen because I'm not sure that the original experiment was like that. But probably just white and black. So what becomes critical in order to understand whether this is only pure rote memory is to see the performance on the first instance any single word was looked at, right? So if it's about memory, the first time you see a real word, it should be just random. Then the second time you remember that you've seen already this word, and then you start being good and press yes all the time. Okay? So the prediction, if this is only a rote memory, it should be that then when you just plot the performance on the words that were seen for the first time during the experiment, they should just be completely random. And this apparently is not the case. So forget about this graph, just concentrate on this. These again, different colors are different baboons. This is the percentage of non-word responses on the first time that a word was seen. Okay? And this is the word, and this is the non-word. So there is a neat difference between the real words and the non-words, even on the first instance that given stimulus was shown. So there was no possible memory for that item in those baboons. And still they were seeing something into the words that they didn't see into the non-words. Of course, with all the caveats that you can think of, the performance is not 0-1, it's not really human-like and whatever, but it's not chance either, so that was the main point. Okay? Do you have a comment, Robbie? No?
Well, I was curious on how the non-words were constructed. But
yeah, I'm going to tell you in a second. Yeah. The non-words were just randomly generated by an algorithm. But what happened with the case is that, of course, again, letter statistics, in this case, the bigram frequency, the mean bigram frequency of those chunks, were obviously lower than those of the words. Okay? Here is measured in a different metric. This, of course, you cannot read this. This is orthographic distance to words. It means how many change in each individual letter you have to make in order to go from the actual stimulus to the first existing word. So how much difference is that non-word to existing words, basically. And this metric goes from 0 to 4 in this case, anyway, there's some dynamic here. And here you see the percentage of accuracy. And as you can see, again, different colors are different baboons. All baboons were sensitive to this variable. Basically, what this graph says is that when the non-word was very similar to words, they were more close to chance. They were more likely to misclassify this as an existing word. When the non-words were very far away from being a word, so they had very strange orthographic appearance, something like Y-U-T-T, something like that in English, for example. They were very good, and pretty much all the time, look at this red guy, this is crazy, 100% correct. Okay? And here for comparison, you have exactly the same sort of relationship plotted in humans. Of course, to a completely different scale. You see that we are slightly less accurate, I would say. But the qualitative relationship between the two variables is very alike. Okay? So that was mainly the point for them to say what these baboons were doing was computing letter statistics in a way that they could have some sort of implicit cue, even the first time that they see any string, to try to guess whether that was an existing word or not. Okay? Again, many different caveats to be made. But the interesting point for me today is that baboons are non-linguistic entities, right? They do not speak any language. They do not have any semantics. Of course, they do not understand what these words mean. And still, just based on the very peripheral, I would even say perceptual characteristic of the stimulus, they were able to disentangle existing entities from non-existing entities. And this cannot be traced back to real language, of course, because language is not there. There's a funny joke that Jonathan Granger tells all the time. No, actually once, and that was actually the reason why it was so funny. He was presenting this data in the Congress a few years back, and then one person in the audience raised their hands and say, why did you specifically choose English as your election language for this study? And he said, oh yeah, then because these baboons can then travel everywhere. Playing on the fact that of course the semantics is not there, right? So they cannot travel anywhere anyway, apart being close in an enclosure. Okay, so right, end of section 2. So what I hope I have convinced you about is that if you stay at the pure form level, so again we're talking about perception of things that happen to be associated to language, but per se are just visual objects, that is visual words, you can find some trace of sensitivity by our brain, and even the brain of our ancestors, if you want, or anyway, other species that are non-humans, that are clearly non-linguistic. You can see sign of this statistical learning happening, at least in some form. Okay? But then you may claim, this is about form, right? So this is about the visual shapes of words. That's not particularly exciting, right? This is not an audience of people interested in perception. They're interested in language. We want to know how these things can get out of this level. And I would claim that there is also some evidence that you could use more or less the same logic to go outside the form and to start computing this time the correlation between form and meaning. Okay? So it's not all about finding what are the existing words versus those that are not, but even finding within the words what these words may mean.
May I ask something before you? It's a trivial question, but just to finish up this chapter.
Yeah.
Are there computational models that are able to distinguish this? Because that's
Jonathan Granger has a computational model of orthographic processing that would be able to model these effects, but is not able to model lots of other effects that are shown in humans. Okay. So my answer would be no, even if there is some disagreement.
I mean, if it's purely a statistical thing, then at least at the form level, it should be doable.
Yeah, absolutely. I guess that if you use any sort of, convolutional networks of unsupervised learning, they should,
That's what you expect.
Yeah. Yeah, but if instead, sorry, I thought you were referring more to the cognitive structure.
No, I really mean if it's a purely statistical thing, then a statistical model should be able to do that, and that's kind of a...
To my knowledge, no one has really tried to actually show this, but it's I share your intuition and this should be the case.
Actually, last year is working on that, telling so there are some data. I'm not sure whether I think there is a proceeding paper about it.
What's the name again, Matt?
Tallinn.
Okay.
I think it's quite recent because I met him last month.
Yeah.
But there is something I will see.
Good to know, yeah. Thanks, Marco, for pointing that out. Right, any other question on this first part? Because now we... Yeah.
Can I?
Sure.
I'm not sure I am understanding, because it's been known for a while that the positional frequency is encoded in the brain, we know where, and influences our ability to read, aloud or lexical decision, whatever. Are you saying that morphology is just encoding bigram or trigram or quadrigram frequency, positional frequency, or you're saying that there is something more on top of that?
Yeah. I would definitely be on the latter side. Okay. I will make this clear at the end, but that's the claim. Again, it's a matter of perspective, not about what reading here really is. What I think is that there may be something going on at the very low level, perceptual level, that is explaining part of the effects that we linguists tend to always overinterpret in a way as something related to how the language works. The language, I mean, like the central levels of processing, like semantics, syntax, and whatever else. The real language, the language, the faculty that distinguishes us from other species, for example. What I'm just saying is that perhaps we have been sort of missing this different look at the same thing. And if we adopt that look, we may find out something that is quite interesting that we're just not seeing right now. So in this case, that visual word identification may be based on this. Think about, for example, all the theories about learning to read, right? None of these theories refers to the fact that one very fundamental ability may just be the ability that these kids have in noticing regularities in the world.
No, but I'm not putting this under doubt. That's clear, crystal clear. And especially, I wonder whether, because you just said that morphemes are just very frequent and they have a particular preferred position. And we know that we automatically extract, as baboons do, positional frequency of bigram and trigrams. This could basically be the same thing as chopping up morphemes.
Well, I don't know how strong of a role this mechanism is playing into our morphological experience. I would say that it's definitely not the whole story. There's lots of things that statistical regularities at the form level cannot explain.
I see.
Yeah. But there are other things that instead they can.
Okay.
So my only point is, let's try to look at this and let's try to take them seriously and to try to see how far we can go in a way. So that would be the idea behind the research program, basically. Let's pretend language is not there, and then letters are just strings of visual events just as any other. Let's see how far we can get in explaining the linguistic events.
Very far. Very little is left to morpheme themselves.
And you will see that now we step into semantics and things becomes even more exciting. I see Marco down there saying, yeah. So yeah, and again, I decided to tell you the story as it unfolds because I think it makes the point a little bit clearer, but it will require you a little bit of patience at the beginning. So what happened is that we were working on this corner corn stuff and the thing that I was telling you at the beginning. And then we noticed that this experiment has been replicated, 20 times now, so we have lots of data available for them. And one thing that at some point we noticed is that there was a very, very consistent side effect that people was just ignoring because it was outside of their interest, but that replicated really consistently in different languages, in different labs and so on. And the effect was the following, that basically, if you ignore the priming part of the experiment, if you just take the targets that happened to be chosen to serve in the transparent form were systematically quicker than the other two conditions. And notice, those are stems. There is no morphology in there. And because those experiments were typically cross-targets, so we had different targets in the different conditions, people was crazy about matching every possible tiny bit you can think of. Letter length, length in letter, frequency, family size, whatever. Everything was super, super matched. And still, there was consistently this main effect of condition. So items that happen to be, I don't know what's happening here, Google password, that's nice. So everything that happened to be in the transparent condition was quicker than the other condition. That was pretty funny, right? Why is that? Okay, I see the distance. And then
What does minute response?
Yeah.
I can get back to that because I'm not sure it's going to be much clearer. But anyway, I will try to make it clearer now. Maybe I should go to this slide, which is a little bit easier to explain. Because you see the design right in front of you. There we go. So this was the classic experiment, okay? So you have priming for deal, corner, dial. Right now, pretend this experiment is not about priming. So forget about what happened to happen before you see the target word. Okay? So suppose now you're comparing just the response time to deal, corn, and dial. This would be a main effect of condition, right? So things that are in this condition are just generally quicker than things that are in this condition, things that are in this condition, independently of whether the prime is related or not. Okay? And this again was a bit funny, because people was trying to counteract this effect to the best of their effort. Because our interest, and those of everybody else, was to match the target word that were in these three conditions for everything you can imagine. Okay, so the response to deal was quicker overall than to corn and to dial, independently of the prime. Okay? Is that a bit clear? Good. And we were sort of scratching our heads onto it and saying, what's going on here? It's very, you know, we could just think that it's sort of a, strange effect that just happened to be there. Or maybe there is something systematic. And because the effect was so really consistent, we were sort of tending to the second.
So the stem of the word that the words that you can use as a stem are faster.
Are faster, yeah. In transparent conditions. And now, maybe I should tell you the second part of the story, things will become clearer by themselves, I hope. So what was the intuition? The intuition was that when you were designing the experiment, right, in order for something to be in the opaque condition, in the corner core condition, needed to have sort of a false morphological neighbor, right, something like corner. And we don't have many of them. Right? So in the language, in Italian, we struggle to have, I think now we have a database of like 95 or 100 items, but it's really scratching on the end of the poem. So basically, everything that could be there was there. And by definition, these words belonged to morphological family, let's call it, that were not super consistent, right? Because at least they had one instance of something that seemed to be a morphological relative, but it was not. Now think about the transparent condition. That's exactly the opposite, right? So words that ended being in that condition were words for which we were able to find a consistent neighbor, right? Something like dealer. So that's the intuition that Marco and Simona Mente had, that basically what happening here is that the words that happen to be in the opaque condition, there is just a mess in understanding what's the meaning behind them. Because they have many different neighbors, and at least some of them are not consistent. Take it from a different perspective. If you look at the form of this word, it's difficult to guess the meaning reliably. If you see deal, you know that whatever comes next, it has something to do with someone selling something to somebody else. If you see corn, then depending on what's come next, this could be Cornwall, so this could be about traveling. It could be corns, it could be corner. So you have basically no idea about the meaning. Okay? So we tried to formalize this a little bit, and I'm sorry that I'm not going to be very formal. I took every equations out of the talk, but if you want, we can go a little bit more in depth. But that was pretty much the idea. We wanted to develop a measure for this intuition. So what we've done, at least at the beginning, it was taking the stem, in this case corn, then get all the words that start with that stem. Morphology was never involved, it's just a pure orthographic form. Then we took their semantic representations, and then we just compute their average similarity. Okay? What you get out of it is what we call the orthography to semantic transparency of a word, which it be considered as the internal consistency of the form family in terms of meaning. Just a different way of saying the same things. How similar in meaning are words that are also similar in form, which ultimately mean how good of a clue to meaning is that particular form. Okay? So what we've done then after that was, again, very simply, we just took from the British Lexicon project the average response time of a large number of English words, and we use the OSC for these English words to see whether this correlated to their identification time. Here we built like basically a regression model where we put some other obvious predictor like word frequency and word length, which we know explain a substantial part of the variance. But even if you have all these predictors, when you put OSC into the model, this is what you get, another very significant predictor. So basically, the story here is that this form to meaning consistency is explaining a unique part of the variance in the time that it takes to you to identify words. If a word points straight away to a very well-identified part of the meaning, it's very easy for you to understand it. Actually, to identify it, because this was lexical decision, so a very non-semantic task, and this is also quite interesting. Yeah, and this again is related to the relationship between the form and the meaning substantially. Okay? We went a little bit on with this, and we tried to find some other validations, if you want, of the OSC effect. So one thing that we've done recently was to see whether these also explain brain responses, some sort of brain responses. In this case, ERPs. Okay? So what we've done, we basically took a database of ERP data, for English obviously, and then we computed the OSC for a number of words that were included in these databases, and then we tried to see whether, again, OSC was not only able to explain the behavior of people, but also their brain response. Okay? This is sort of ongoing work, so I don't have very final data, but this is already something that I think is quite interesting. Of course, you cannot see this. This is the OSC measure on the x-axis. On the y-axis, I forgot to say, these are ERP data about sentence reading. So this is another difference as compared to the previous one. The previous one was single word identification. Here instead is more natural reading, right? So people was reading real sentences to gauge the meaning, basically. And we know that one very strong predictor of the ERP and in general of the behavior of people in this condition is the predictability of the upcoming words. If your context gives all the information, right? Yesterday morning I was very, no, this is not very good. I'm very bad at examples and so yeah, I could recycle this for the opposite example. Yesterday morning I was very hungry and then I ate, it can be banana, it can be sandwich, it can be chocolate, it can be whatever you want. But if you say Rovereto is a very good footballer and last season he scored 27, everyone knows that I'm going to say goal, right? So in one case you have very different reactions from the other case. And this is very well established effects in eye tracking, in ERP, in behavior, in whatever. This variable is actually tracking this effect. So what we got from this preliminary analysis is an interaction between OSC and this prediction value. So basically what happens is that depending on the level of the predictability of the following words, you get different effects of OSC. Right? You can see this, that the third dimension of the graph, basically the color code, is the amount of brain signal that you get. And you can see that, for example, if you go at high level of predictability, the color is very constant if you go in this direction. Meaning that if you change the OSC, the brain is not responding much. But if you go here, sort of intermediate level of predictability, you see that the color tends to change way more. And if you go down here, when predictability is even lower, you really get huge effect. So this seems to say, if you can predict the coming word and the meaning of what I'm reading up based on sort of higher level predictions, like which word is coming next, then I don't care too much about OSC. But if I'm not able to make a very good prediction of what's coming next, then I rely on whatever information I can get, even the internal consistency of the family of that word. Second thing on which I want to draw your attention, the two ERP components on which we find the effect was N400, which is the classic, very well-known lexical component of ERPs, so this was not particularly surprising, but quite interesting, even with LAN. LAN is a rather early thing. It happens to peak around 200 milliseconds, so it's very early on. And still, it seems that even if you're very early in processing, you get this modulation effect.
What is LAN?
It is LAN, we know that it's
Left anterior negative.
left and what is LAN? Sorry. I thought you said but is LAN, and I said yeah. Left anterior negative, yeah. It's actually a little bit of a strange, I would say, ERP component. It's typically associated even to in some experiments has been associated to syntactic strange violations. Actually, I would say more morphological than syntactic. The typical case is like a disagreement in number. When you hear sentences like, this morning I ate 2 apples, and you miss the S, or 1 apples. When you get to the violations, you get this very early reaction from the system. So it's not very clear what it really tracks. But I would say that not even the N400 is very clear.
So did you try the N170?
No.
The typical word.
Marco, do you remember whether we had this?
No, we didn't try.
I don't think
yet, at least.
Just because it's typically associated to word recognition, to activation of the visual morpheme area. So if you think that this kind of effect can go down to the level of recognition of the word, then maybe it's possible to retrieve it even slightly earlier.
Thanks for the tip. Yeah, the thing is that for the moment we just do basically how did this database look like is that they release basically the raw just pre-processed data, but also already the components already computed. And for now we just use the components, so we didn't have this one. We used everything that we had available. But I think that we had the P60, the P600, but nothing later than that. I'm not sure. I think we had the ELAN and 400, maybe some.
I'm talking about this N170. So it's
very
early.
I don't think that we had the N170. But we'll check it out, and by the way, we can obviously reconstruct from the signal from the beginning. This is what we are working on now. Okay, so just another example of this, and then I close up everything. OSC has also been shown to basically have a counterpart in phonology, right? So for Italian, it's very obvious. I mean, OSC is essentially also a phonological semantic consistency because the correspondence between phonemes and graphemes is so strict that everything that is predictable on the basis of the graphemes will also be predictable on the basis of the phonemes. But for languages like English, where the correspondence is way looser, you can think about computing the two things. And that's exactly what Marco Simona, together with Simone Sulpizio, have done. And before looking at the graph, sorry, I take it out to distract you, they were basically able to show that you also have a phonology to semantic consistency. So when you're able to consider a sample of words where the two measures do not really correlate too strongly, you see an effect of orthographic semantic consistency and also an effect of phonological semantic consistency. There is even an interaction between the two effects, which is illustrated here. So this is OSC. So this is the orthographic semantic consistency score. This is low, this is high. Okay, so high predictability, low predictability. This is response time. And then we plotted, they have plotted actually, not me, the relationship between OSC and the response time at different level of phonological consistency. And again, this is low phonological consistency, this is high phonological consistency. So it's a little bit of a complex graph, I can drive you through this. Basically the story is that when one of the two is low, so you cannot get much information from it, you go to the other. You're so much starving about this kind of information that you search for it everywhere. Another important thing to underline, this was visual word identification times. So phonology was not even required to be computed by the task. Still, we were sort of implicitly computing. And this is the effect. For example, if you go here, basically this is OSC is very low. So you get no prediction on the basis of orthography, and see how the difference in the response time between low and high phonological consistency is big. So you have a big effect of phonological consistency where the orthography doesn't tell you much. If you go here, orthography is very informative. Pretty much you have everything you can. Look at the difference between different levels of phonological consistency, virtually nothing. Okay? They even went on and tried to see whether there was any sort of predominant role by either one of the two, and it turns out that phonology seems to be predominant, which is quite interesting because the task was purely visual. So everyone, I mean, at least I would have predicted the opposite. I would have predicted that orthography is the very core of the story, and then if you cannot get much from the task that you're running now, you go to phonology. Seems to be the other way around a little bit more. You first go to phonology, and then you get into orthography. Here we can speculate hours. I think that the most interesting perspective that you can have starts from a very basic consideration that language is spoken, right? So from this point of view, it's not particularly surprising that you're going there. But, if you really think about it, this would mean that all this may mean, not necessarily imply that, but is consistent with, the idea that you get all these statistics even before you get to be a good reader. So maybe we are computing this at a very, very early age. Of course, the two things do not go together. But if you think that the explanation for why phonology is predominant to orthography sort of puts you in a condition to say, well, maybe it's because we already knew something, and when some more information gets in, if it doesn't correlate with what I already know, then of course I pay attention. But if it does, then I know it already. Why is that interesting? Which to me is very surprising and opens lots of, funny thoughts. Okay, I had another little bit, but I will skip it because it's not adding anything to the story. So getting back from where we started, the core of the thing is what I showed at the beginning. So again, I hope I convinced you that I think it's interesting and a worth scientific endeavor to try to look at least a visual word identification in this perspective, right? And the data that Marco, Simona, and Simone have obtained also showed us that maybe there may be something even in phonology. And quite interesting, this sort of statistical learning approach can go over form, can also start tracking some relationship between form and meaning. Very important last bit, you have a can in all of these single words, and we get to the point you were discussing earlier on. This is a possible look into the system, not the only one, and at least for now I'm absolutely sure that we cannot claim this is the whole story, and it's actually very unlikely to be the whole story. Still, I think there is something to be sort of dig out that we haven't done yet, and that maybe can sort of helping us shedding out a little bit more light on a general theory of language, or at least how our brains come to deal with it. Okay? So before I close, just let me say thank to, in particular, Marco and Simona, who have been my main collaborators on all of this work, and then Cathy Russell and Colin Davis, with which I've done basically the work on English that I showed in the beginning. And that's it. So thanks to you for your
Well, thanks for the interesting talk, and other questions?
I love it, it's fantastic. Do you have a database where you have encoded and tagged all the words in Italian with these orthography to semantic?
I leave you, Marco, go ahead, he's taking care of all this.
We have it in English.
You have it in English?
Yeah,
Okay,
and
that's
it's
great.
about to be released. Hopefully, fingers crossed, it'll be presented.
No, but also because I think of the inter-language differences in grapheme to phoneme transparency that influences that much speed and ease of acquisition of reading. Think about doing exactly the same kinds of analysis by using these features. That would be a mean to show that all this enters into the reading system and makes it easy or not easy to learn to read.
Absolutely. And another very interesting thing to me, which is kind of related to this point, is what about non-alphabetic languages? If that's true, if the real hypothesis is that basically the brain is so starving for correlations that it finds out whatever it finds, it should apply the same to languages where it's way less obvious to play around with this, right? Because with letters it's very easy. I mean, you have it's not very easy, but you can easily imagine that you have very well identifiable individual objects, so it's easy to identify them individually and then to track for the statistics. But what about the strokes in the Chinese language, for example? I don't even know whether there is a statistical structure in there. And I think that showing some of these effects in one of those languages would be a very good addition for the story. At least in terms of their generality, because of course this may apply well to alphabetic languages, but only languages where the visual units of the reading are not so clear, both perceptually and linguistically, because I don't know much about Chinese, but I've heard that people is also not very clear about not only which is the phonological unit, but even the morphological unit at some point. If you can draw a distinction where in this kind of scripts, which is remain to be seen.
With respect to this last point, I think you could actually do a computational model where you just show use a convolutional network to actually look at the ideograms behind words and then try to compare the distance between one character and the other, and in terms of the representation that the convolutional network gives you, and then try to replicate that.
Yeah.
Quite interesting. One thing that I was a couple of things. One is this focus on frequency, of course, makes you wonder about the gigantic difference that you get between affixes and stems, because the frequency is so vastly different that, but on the other hand, that didn't come out. I mean, from we were talking about the prediction of various things in the first experiment you mentioned, but then you also did the attempt with the compound cases. But of course, stems are so much more infrequent than affixes that I would have expected a greater difference. And if you have any comment on that. And also another question that I was wondering about, when you were looking at prefixes and affixes, did you also try with the affix in isolation, that is to only show ness, and then to try to look whether that primes? Because you could imagine that on the one hand, so ness at that point becomes a prefix and so at the beginning and an end. Does that have a blocking effect? How does that work? That would be an interesting.
So I respond first to the second question, just because I remember that very well. No, I've never looked myself, but there's a priming experiment by John Andoni Duñabetia, who ran it in Spanish, and I think they had like, I don't know, maybe like a 4-experiment paper in which they were showing suffix priming, and they started off with word, so something like kindness or I told you a very bad example. Anything else, ness. And then they tried to destroy the word structure. So in the second experiment, they used the suffix in isolation. In another experiment, they substituted the stem with a string of Ashmat, for example, taking away all the linguistic information, and it worked in all situations. I also have another experiment where we shown mask priming with suffixes, and that worked out very well in English. And now there's a student of mine at SISSA who's Slovene, so we're trying the same in Slovene, which is very interesting because they have way longer inflection. This was all done on derivation. So now they've tried with inflection, and it even seems that you get exactly the same amount of priming that you get with the stem, when the two things are the same length.
Yeah, and the frequency is just,
And the frequency, I mean, we didn't compute it because in Slovene it's just a nightmare. But now we found out that we have the WAC Slovene version, so maybe we're going to be able to compute good stats out of it. For now, we haven't tried with the numbers, but yeah, I bet it's the same as for any other languages, that the suffixes themselves are so much more frequent than any stem you can think of. And it's very interesting to me that it isn't even going to the inflectional system, because people have been claiming lots of difference between the two, between derivation and inflection. And at least this is all mass priming, so of course it's really tapping on a very early level of analysis. I bet that if you have some a little bit less shallow task, something that involves more semantics or even syntax, you may get something different. But from the purely perceptual point of view, I don't think there's much difference as for the data that are out now.
Wait, no. Yes, I'm last.
Go. First, okay. So I don't know how much. It's more a brain question, I guess. At what level do you think this learning is taking place? Because what you were saying before about the influence of phonology during visual word identification and lexical decision. So if it's based on statistical learning about letters, right, going together, or phonemes going together, that seems very different from what the baboons were learning, right? That they had just one modality, and that was and in principle, this connection, may take place in early visual areas, right? Very early. But in this case, it can be that you have somehow statistical learning in two different parts of the brain, one auditory one, and a visual one, and then you go to search first in the auditory one for phonology, and then if you don't find it, you get information. Or it might be that there is some more abstract level of representation. I don't know if you have never thought about
we are actually running, well, running is a probably a little bit more pretentious now. But we are thinking about running such an experiment, we are very curious. The difficult thing is that, of course, everything that I've shown now is like a snapshot of completely mature systems. So we have completely missed, if you want, the learning fact as it happens. So now the series of experiments that we are running now in the lab is basically playing around with artificial lexicons, in which we build ourselves the kind of statistical regularities that we think are most effective. And this is going to be all new for the participants, so they are really learning on the fly. And one of the things we want to do is try to have probably an MEG experiment where we try to address this. So go look exactly at the time and hopefully space of about just addressing the question that you asked.
So you can add the two modalities?
You can add the two modalities, You can actually, I'm not sure whether it would be easy to manipulate the two independently. But one thing that you can easily do, for example, is just having the learning happening in the two modalities, right? Versus one. In some experiments, there's lots of learning experiments. I've just mentioned it in passing at the beginning, where people is already doing that. In a way that I think it's not very effective for showing this effect because it's very guided, it's very formal. So the experiment is basically you come into the lab and the experimenter tell you, okay, now there's a new language for you. This is pig. Repeat this with me. Pig, blah, blah, blah. So it's very school-like. So I don't think it encourages a lot this sort of implicit learning. So now what we're trying to do is using the sort of the baboon more type of experiments. So people have to guess themselves what are the real words and not the real words. And you can do this in one modality, you can do this in two modality, and you can make the two modality go together or not. We still don't know what happens, but I think it's a very interesting question. My intuition right now is that this is more like a perceptual mechanism that sort of gets inherited by later levels of processing, if you want. I would not think that, I don't know, structures like the frontal lobe, for example, is really computing independently of what happens early on in the stream, this kind of stuff. Because on the perceptual level, this sort of statistical learning is already very well established, right? It's nothing particularly new. The new thing is considering, if you want seriously, this hypothesis and see how much this affects other domain, or better, domain that were believed to be other until a few years back, such as, again, language based. So, although, you had this phonology over orthography piece of evidence that sort of may suggest you that there is something special about that. But again, I mean, this gets close to the question that we are after with the blind, right? Is it about the modality, or is it just about the way of computing things? And then if the things comes along visually, then you get it visually. If it comes along acoustically, you get acoustically. If it comes haptically, you get it haptically.
I mean, if for instance you look at the 170 components, right, which is the one where usually the WFA fires, which is active mostly when you read words, not when you listen to it. I mean, sometimes you find it, but and then you see this effect of phonology in there is because I don't know. It's maybe it's
Thank you. This is a very good suggestion. If this ends at 170, we didn't really think about it, so we're gonna look into it. Thanks a lot.
One last question. Sorry, but
before you were saying, well, statistical learning might not be the whole story, and so the only other suggestion, the only other option I thought would be like universal grammar, but there's no specific mechanism for acquiring orthography or phonological patterns. So I was wondering if there's any other third option you were thinking of, because how we could acquire this knowledge without statistical learning.
Not that I can think of right now on the spot. No, I don't know. I really think I would prefer to remain agnostic, if you want, at what happens, at the later level of analysis. Of course, there are also some sort of statistical regularities that can track some of these more, if you want, central features. I was talking to Sandro earlier on, and we were mentioning this work about, for example, the distinction between mass and count nouns, which is again lexical, but it's typically considered to be like a syntactic aspect of the lexicon. And here again, people that is looking into it and into the sort of information that you can get about a distinction just based on the visual features, for example, or from how the words occur in the language, you can also see cues there. So who knows, maybe this is part of the learning thing, and we have something that is sort of prone, which would be the genetically based, basically. So what the evolution of the species gave us, the sort of scaffold on which we can get information. But of course, we don't know that information. Information must come bottom up. So maybe statistical learning is exactly the mechanism that put things into place into this scaffold that evolution has provided us with. Whether this is universal grammar, I wouldn't say so, just because it's not very fashionable anymore right now. But I don't want to take any stance, because I really don't know exactly whether this would be something that, you know, Chomskyans would be happy about, or they would say, oh no, that's not what we mean by UG. I hope this addresses. Thank you.
So thanks again, Davide, for the talk.
Thanks to you.
We're going for dinner this evening, and there is a table book, and
at Palazzo di Chitarra in Piazza the other one, the other Piazza.
so if you want to come, Sandro is organized.
Yeah, so just it's the lectures.
Qui spengo, Sandro, come... Premo questo? Sandro, spengo qui.